Look inside the silicon of a modern smartphone, and you'll find a network of pathways engineered to process data at staggering speeds. But when developers try to run dense neural networks inside this hardware, the system routinely chokes. There is a common misunderstanding regarding local AI inference. The intuitive assumption is that mobile edge devices simply lack the raw compute power to handle complex models. But processing power is no longer the primary bottleneck. This diagram represents the standard layout of a mobile system on chip. You have dedicated blocks for the CPU, the GPU, the neural processing unit, storage, and RAM. The actual choke point for local AI sits right here, between storage and active memory. Standard large language models require massive amounts of memory. To run inference, traditional engines attempt to load the model's full weights from storage directly into RAM, rapidly saturating the available space. Mobile operating systems are explicitly engineered to prevent this. Their memory managers are highly aggressive, and the moment an application spikes in RAM usage, the OS intervenes and kills the process to save battery. Porting a standard server-side AI architecture directly to a mobile device ignores this hard kill threshold, resulting in brittle software prone to crashing in the background. To achieve reliable local inference, the software architecture must treat mobile hardware constraints as first-class design parameters, rather than trying to force a desktop solution onto a phone. This brings us to Cactus, a low-latency inference engine built specifically to navigate this constrained environment. Instead of defaulting to general-purpose GPUs like most engines, Cactus explicitly targets the neural processing unit. And to bypass the strict RAM limits, it changes the physical mechanism for retrieving model weights. Reliable edge performance requires discarding the traditional inference pipeline entirely and rebuilding both the memory and compute layers from the ground up. This flow diagram contrasts the standard GGUF approach with Cactus zero-copy architecture. Traditional engines attempt to load the entire model into active memory before reasoning begins. With zero copy, weights remain at rest in storage. The engine pulls specific tensors exactly when required for reasoning. This fractional, just-in-time extraction ensures the application's memory footprint never spikes, keeping it safely below the operating system's kill threshold. However, standard model formats are not structured to support this kind of localized, piecemeal extraction on mobile hardware. To make this mapping effective, Cactus transitioned away from the traditional GGUF format, developing their own proprietary Cactid file format, which enables precise tensor targeting on the edge. Changing the format and utilizing zero-copy mapping lets developers access a large model's full reasoning power without triggering an OS background termination. With the memory bottleneck solved, the next constraint is the physical computation of the data on the silicon. Here, we're looking at the NPU block and its internal matrix multiplication units. Most local AI frameworks route tasks through the general-purpose GPU. This creates friction, requiring software translation layers that bloat the process. Cactus removes this friction, establishing direct communication pathways straight to the NPU's matrix multiplication units. This architecture aligns with modern hardware realities. Companies like Apple, Qualcomm, and MediaTek are all shipping chips heavily equipped with this dedicated neural silicon. Prioritizing direct NPU communication over generalized GPU compute is the specific method for achieving sub-second latency on heavily constrained mobile devices. Engineers must accept a physical limit. Regardless of how memory and compute architecture are optimized, an edge device eventually hits a strict reasoning ceiling. This creates a dilemma. Do you build around a fast but limited local model, or a capable but expensive high-latency cloud model? Cactus addresses this through a hybrid router. This flowchart outlines an automated system designed to handle failover dynamically. Simple prompts are instantly diverted locally. Execution is fast, private, and incurs zero server costs. The system continuously monitors confidence levels. If a task is too complex or demands a massive context window, the failover triggers. The router automatically hands the request off to a frontier cloud model, like Gemini, to process the heavy lifting. For the engineer, the application codebase remains entirely unchanged. The engine manages all the complex routing logic in the background. Implementing a hybrid router moves local AI from an unreliable experiment to a production-ready system, capable of handling complex edge cases without breaking the user experience. Theoretical architecture only matters if it holds up in practice. To validate this, we look at a standard Swift application built for real-time speech transcription. The test parameters require running live streaming transcription natively on an older edge device, specifically an iPhone 12 Pro. The setup tests the localized parakeet speech model running on-device against a cloud-based Gemini 2.5 Flash alternative. This chart displays the resulting latency. Execution on the local NPU with Parakeet averages 260 milliseconds, while cloud execution using Gemini averages 2,000 milliseconds. A server round trip takes nearly 10 times longer than processing the exact same task on local edge hardware. 2,000 milliseconds of latency is too sluggish for live transcription, but that cloud route remains vital as a fallback for asynchronous, heavy analysis tasks. For real-time functionality, aggressive on-device optimization is a strict technical requirement. It is the only way to achieve acceptable latency for the end user. Achieving low-latency edge AI requires structural discipline. You cannot just compress server-grade models, force them onto mobile hardware, and expect stability. This master schematic illustrates the complete end-to-end system architecture required for native edge processing. First, zero-copy memory mapping is mandatory to satisfy the strict limitations of the mobile operating system's memory manager. Second, direct NPU targeting is required to strip away translation bloat and harness the hardware's dedicated matrix multipliers. Third, hybrid cloud routing is necessary to push past the local reasoning ceiling, seamlessly handling overflow without requiring the engineer to rewrite application logic. By designing software that respects hardware constraints, architectures like Cactus allow developers to deploy high-speed intelligence directly into the user's pocket.